When you hear the words computer science, what pops into your head? Probably a dark room, someone in a hoodie, just lines and lines of glowing green code, right? I mean, sure, that's part of it, but saying that's all there is to it is kind of like saying astronomy is just about looking through a telescope. The reality is so much bigger and, honestly, a whole lot more interesting.
Let's just start with this classic quote from the legendary computer scientist Edsger Dijkstra. He said, "Computer science is no more about computers than astronomy is about telescopes." Think about that for a second. That's a huge idea. It's telling us that to computer, that's just the tool. It's not the actual thing we're studying.
So, okay, if it's not really about the machine itself, then what is it about? What's the big question that sits at the very heart of this field that has, completely changed our world?
Over the next few minutes, we're going to try to build a totally new way of thinking about computer science. We'll start with its core question, then we'll explore its three main pillars: the theory, the applications, and the systems that make it all run. And then we're going to wrap up with three mind-bendingly simple insights that make the whole thing possible. All right, so before we get into all the different branches and fields, we need to get on the same page about what computer science is fundamentally trying to do.
So, at its absolute core, computer science is the study of three things: computation, information, and automation. Now, did you notice what's missing from that definition? The word computer. It's not in there. That's because it's about the how, not the what. It's about the processes, the data, and the principles of how we can make tasks happen automatically.
And all of that, it really just boils down to one simple but incredibly powerful question. What can be automated? This is it. This is the North Star for all of computer science. It guides everything from the simplest pocket calculator to the most complex artificial intelligence. So keep this question in your head, because everything we're about to talk about is, in some way, an attempt to answer it.
Now let's jump into that first pillar, the theoretical foundation. You can think of this as the mathematical soul of computing. It's the abstract, invisible bedrock that everything else is built on top of.
The goal here isn't to build the next viral app. Not at all. It's about asking much, much deeper questions. Questions like, what is even possible for a machine to compute? And maybe even more important, are there some problems that are just impossible to solve, period? This is where we explore the absolute outer limits of what computation can do.
And this theoretical side covers a huge range of fields. You've got the theory of computation, which dives into those absolute limits we just mentioned. There's information and coding theory, which asks how we can represent and squeeze down data. How to make a massive movie file small enough to stream online. Then you have algorithms and data structures. These are like the fundamental recipes and ingredients for solving any problem efficiently. And even programming language theory, which studies the very design of the languages we use to talk to computers.
And all this leads us to one of the biggest, most famous, unsolved mysteries in all of science, the P versus NP problem. So think of it this way. Some problems are pretty easy for a computer to solve, like finding the absolute shortest route on a map. We call those P problems. But then there are other problems that are super hard to solve, but if I just give you an answer, it's really easy to check if it's right. A finished Sudoku puzzle is a perfect example of this. Those are NP problems. So the million-dollar question is every problem that's easy to check also secretly easy to solve? And the answer is, we still have no idea.
So that's the theory. Super abstract, super important. Now let's look at how all that theory actually gets applied in the real world with our second pillar, building the digital world. This is where those abstract ideas become the tools that, we use every single day. I mean, this is the side of computer science you already know. It's the apps on your phone, the websites you're browsing, the video games you play. It's the incredibly complex software that runs everything from global financial markets to life-saving medical equipment. This is where the rubber meets the road.
Yeah, you're going to recognize a lot of these fields. We've got AI and machine learning, which is powering everything from your phone's camera to self-driving cars. There's software engineering, the art and science of building absolutely massive, reliable software systems that don't crash. You've got computer graphics, the magic that brings movies and video games to life with stunning visuals. And then human-computer interaction, which is all about designing technology that feels intuitive and, just feels good for us humans to use.
But wait, how does all of that amazing software, all those apps and AIs, how do they actually run on a physical hunk of metal and silicon? Well, that brings us to our third and final pillar, making machines work. This is the crucial bridge that connects the world of software to the world of hardware.
This area is all about the underlying infrastructure, the plumbing, the engine room.
It answers the most fundamental questions, like how does software actually talk to the hardware? How is memory managed so you can run 10 things at once? How is your information sent securely across the globe? Seriously, without this pillar, all that amazing software would just be, well, a bunch of good ideas.
This is the world of computer architecture, the actual blueprint for the processors inside your devices. It's your operating system, like Windows or Mac OS, which acts like a master conductor, letting you run multiple apps at the same time. It's the computer networks that literally form the internet, connecting all of us together. And of course, it's computer security and cryptography, the folks working tirelessly behind the scenes to keep our systems and our data safe.
Okay, so we've got theory, application, and systems. 3 huge, incredibly complex domains. But here's the truly wild part. All of this complexity, it's all built on top of just a few breathtakingly simple and elegant ideas. Sometimes they're called the 3 great insights of computer science.
The first insight is the power of 2. That's right. Every single piece of information, from this video you're watching to a song to the entire human genome, it can all be represented using just 2 symbols, 0 and 1, on and off. That's it. This incredibly simple idea of binary is the universal language that underpins absolutely everything in the digital world.
The second insight is the power of 5. It turns out that any algorithm, I don't care how complex it is, can be broken down into just 5 basic actions. Move left, move right, read a symbol, print a 0, and print a 1. That's it. With just those 5 ridiculously simple instructions, we can build any computation you can possibly imagine, from adding 2 numbers together to simulating the entire universe.
And the final insight is the power of 3. You only need 3 ways to combine those 5 simple actions. First, there's sequence. Do this and then do that. Simple. Then there's selection. If some condition is true, do one thing or else do another. And finally, repetition. While a condition is true, just keep doing this thing over and over again. And that's it. Every single program you've ever used is just a clever, nested arrangement of those 3 basic structures.
Just let that sink in for a moment. 2 symbols, 5 actions, and 3 ways to combine them. From that almost comical level of simplicity, we have built the entire digital world. Everything from your web browser to the most advanced artificial intelligence. It's just an incredible testament to how profound, world-changing complexity can emerge from the simplest possible rules.
Which brings us right back to where we started. The fundamental question of computer science is, what can be automated? We've automated calculation, we've automated communication, we've even started to automate parts of our own creativity. The question that this field will just keep exploring with its foundation in theory, its expression in applications, and its power through systems is, what's next?